Acid-Base Analysis, a Lecture in Verse by Paul Fine. So you want to be a star, impressing everyone you know. In short, to win the human race. You don't need to be on Twitter or to have a TV show. Just understand your acid base. It's not merely that this knowledge will provide you fame and wealth, serenity, delight, and bliss. It will also help you recognize departures from good health, conditions you don't want to miss. It's really not that tricky, but it's crucial that the plan helps even those who struggle with a short attention span. Use this step-by-step approach that helps you cover all the bases, and soon you will be solving the most intricate of cases. We'll review some basic questions asked in all investigations, and some others that we only need in certain situations. So that is our agenda. It is time to get immersed. Let's get started with the questions now, beginning with the first. Number 1. Is the patient's blood acidemic or alkalemic? It's important to remember, if you want to pass that quiz, that the first step is to look at what the pH value is. It is 7.40, as we say in academia, that splits the ones with acid from the ones with alkalemia. And remember that the emia just tells the net effect, the sum of pH pushes from derangements we'll detect. Each one of them's an osis, and it's helpful to remind there may be only one, but 2 or 3 can be combined. Question number 2. Is the primary disturbance metabolic or respiratory? Next you find the major problem, which is done as you review the levels of the bicarb in the patient's CO2. We want acid-base analysis quite accurate and formal, so it's crucial that we start with an idea of what is normal. For the bicarb, a result of 24 will ring that bell. A CO2 of 40 is the rule when all is well. The bicarb's the result of metabolic execution. The CO2's the respiratory system's contribution. The two of these are critical in acid-base disease, so we may as well refer to them together as the keys. This seems the proper time for me to mention compensation, a bit of our design that one might view with admiration. When either system perpetrates a pH indiscretion, the other tries correction in the opposite direction. This effort is impressive, but will never quite succeed in fully making up for the original misdeed. If the keys are low within an alkalemic situation, the pathologic problem must be hyperventilation. Exaggerated breathing pushes down the CO2. The bicarb ends up low when compensation has come through. And what makes certain people prone to hyperventilation? Anxiety and brutal pain and chronic aspiration, salicylate, progesterone, anemia, cirrhosis, CHF, pneumonia, interstitial lung fibrosis, a pulmonary embolus, a decreased PO2. Of course, there are some more, but that's enough for this review. If a patient's alkalemic and you find both keys are high, metabolic alkalosis is the answer you'll supply. Its most distinctive feature is a bicarb elevation. The respiratory answer is to decrease ventilation. Metabolic alkaloses are well known for their variety. The many diuretics have a special notoriety. There's vomiting and comparably the use of NG suction, a surplus of aldosterone, potassium reduction, bicarbonate ingestion when the renal function's bad. Contraction of the volume is the last one we will add. For an acidemic patient, if we see both keys are high, then hypoventilation has to be the reason why. The climb in CO2 provides the clue you can't forget. Then the metabolic system keeps more bicarb to offset. For this respiratory acidosis, let us now address causation. Neuromuscular conditions that can weaken ventilation. a foreign body blockage of the respiratory tree, severe fibrotic lung disease, and some COPD. There are nervous system problems that blunt respiratory drive, and opiates, of course, may do the same when they arrive. For an acidemic patient, when we find both keys are low, metabolic acidosis is the label we'll bestow. Reduction of the bicarb is that ailment's declaration. The CO2 is then lowered by the lungs in compensation. Metabolic acidoses can be further subdivided. By the sodium, the chloride, and the bicarb, you'll be guided. Just start out with the first one, then subtract the other two. The result is called the anion gap, though gap alone will do. To have a gap is normal. Let me share the reason why. The sodium quite dominates our cation supply, but bicarbonate and chloride do not have as much success, representing all the anionic charges we possess. For those with metabolic acidosis, we explore just how the gap compares to what it used to be before. If we do not have a baseline gap to which we can compare, the population norm is an alternative that's fair. This normal gap's as high as 12, but please heed this instruction. It's less with myeloma or an albumin reduction. And finally now, the diagnostic list for which you've waited: metabolic acidosis when the gap is elevated. Salicylates, uremia, and ketoacidosis. A lactic acid excess is another diagnosis. Methanol and antifreeze each have a grim prognosis. It probably won't surprise you that the list will have to change when the patient has a gap that is within the normal range. There's RTA, you get your pick, types 1 and 2 and 4, and also diarrhea, a disease we all deplore. And what about type 3? If you are curious, don't despair. It's 1 and 2 together, and it's really very rare. Let us now review the patterns of pH and R2 keys and the way they guide analysis of acid-base disease. For now, we are assuming still, before things get complex, that there's only one disturbance and the compensation checks. These three voices change in sync when it's a metabolic choir, all pitched down in acidosis, but with alkalosis, higher. But with respiratory issues, they diverge in where they go. When it's hypoventilation, keys are high but pH low. When there's hyperventilation, as the lungs increase their pace, pH rises toward soprano, but the keys move toward the bass. The steps that we've discussed so far serve nicely to reveal a primary disturbance that we can then attack with zeal. But there's more we need to analyze, and now we have in store some subtle calculations that will tell us if there's more. Question 3a. If the primary disturbance is a metabolic acidosis, is the anion gap elevated? Metabolic acidoses crave additional assessment. 3 supplemental steps in which we need to make investment. And here's some lovely news to get us started with a clap. We've already done the first of these to calculate the gap. Question 3b. If the primary disturbance is a metabolic acidosis, is the respiratory compensation appropriate? In the second, we return to respiratory compensation, where a yes or no is not enough, though often a temptation. The degree of compensation should be always in proportion to the level of a bicarb's metabolical distortion. The formula of Winter is a recommended tool to determine if the CO2 is following this rule. It's 1.5 times bicarb, adding 8 that we perceive, to represent the CO2 the body should achieve. But nothing's that precise, so it's important to confide that the answer has an error range of 2 on either side. If the patient's CO2 is sadly higher than predicted, there's another diagnosis with which he has been afflicted. A respiratory acidosis is the new one he'll be getting, for Winter redefines what counts as normal in this setting. In contrast, if the CO2 is pushed lower than expected, we cannot praise the lungs for doing more than was projected. There's a respiratory alkalosis. That's the phrase that you should know. It's the one we always use when CO2 becomes too low. 2 extra steps so far for metabolic acidosis. Would you come up with these questions if subjected to hypnosis? Is the A gap elevated? Is the compensation right? Now a final question beckons. Let us bring it next to light. Question 3C. If the primary disturbance is a metabolic acidosis, if the anion gap is elevated, can that process account for the entire change in bicarbonate, or must an additional metabolic process, a non-gap acidosis, or a metabolic alkalosis, be invoked? This question's only needed when the gap is running high. If you find that it is normal, you may simply pass it by. We are asking if the gap-enhancing process we inferred can account for the entire change in bicarb that occurred. Here's the trick that makes it possible. The increase in the gap will approximate the bicarbs that are taken off the map. If the gap is raised by 4, it is 4 bicarbs that were lost. If the gap is 8 points higher, then 8 bicarbs were the cost. The approach will make more sense if your experience is ample, so I'll take this opportunity to teach it through example. If the bicarb is 11 and the gap is now 14, we first assess the change in gap, just part of our routine. If we find no patient baseline when into the past we delve, we'll compare that gap of 14 to a normal gap of 12. The difference in the gap is only 2, and what that means is that now it's time to see what's going on behind the scenes. Remember, when it's normal, that the bicarb's 24. If the level's now 11, that is 13 out the door. But how many missing bicarbs did the gap disorder cause? You'll say it's 2, the change in gap. Then welcome the applause. Now let's put it all together. Where the bicarb is concerned, the net reduction's 13, but the verdict has returned that the A-gap acidosis can account for only 2, so another process must have made 11 bid adieu. Bicarbonate departure with no increase in the gap? A non-gap acidosis is the gift we last unwrap. And so, in our example, we've uncovered, once immersed, an important diagnosis not too obvious at first. And that extra diagnosis isn't trivial at all. The non-gap acidosis stole more bicarb, you'll recall. I believe it would be wise to give you one example more to make this step seem easier and not so much a chore. Let's say the gap is 35. Quite striking, you'll agree. With bicarbonate decreased to 10. Now let's attack with glee. The first thing you might notice is the gap is quite impressive, much more than in the prior case, perhaps a bit excessive. If we find no baseline value in the records we can see, we'll compare this gap to 12 and call the difference 23. So 23 must also be how much the bicarb fell from this metabolic process that convinced the gap to swell. But overall, the bicarb dropped from 24 to 10, a decline of 14 only. So we must declare again that the A-gap acidosis can't explain it on its own. Some extra bicarb must have been delivered, we have shown. You'll see, I hope, unless you have a nearly blinding ptosis, that this bicarb raising points to metabolic alkalosis, a process that offsets somewhat the bicarb loss we'd get if the A-gap acidosis had been solo, not duet. I'll admit, before we're through, I didn't want to be sadistic, so I've made this last analysis a little bit simplistic. The change in gap and bicarb loss aren't always one-to-one, so temper your conclusions when the math at last is done. If that final step, comparing, shows a difference, but it's small, there may not be another diagnosis after all. Number 4. If the primary disturbance is a metabolic alkalosis, is the respiratory compensation appropriate? Here it's crucial that you know that we have left the winter season. You must restrict that rule to acidosis, for good reason. Don't be tempted to employ it when pH and keys are high. Metabolic alkaloses have their own rules that apply. For them, a major change in CO2 will not accrue. Too much underventilation and we'd threaten PO2. So the change in CO2 is much less likely to impress, just 0.6 up for every bicarb in excess. Question 5. If the primary disturbance is respiratory, is it chronic or acute? For acute respiratory acidosis, the expected change in bicarbonate equals the change in PCO2 divided by 10. For a chronic respiratory acidosis, the expected change in bicarbonate equals 3 times the change in PCO2 divided by 10. For an acute respiratory alkalosis, the expected change in bicarbonate equals 2 times the change in PCO2 divided by 10. And for a chronic respiratory alkalosis, the expected change in bicarbonate equals 4 times the change in PCO2 divided by 10. And now you will be pleased to learn we've reached our closing task, to review the final question that we'll sometimes need to ask. If the primary disturbance wears a respiratory suit, how best can we determine if it's chronic or acute? We need to talk again of compensation that's received, specifically the time it takes before it is achieved. Adjustments in the breathing fairly quickly can be made, so the formula of Winter rather promptly is obeyed. But metabolic changes take much longer to complete. There's initial pH buffering, but its impact is petite. The kidney's own response will finish 3 to 5 days later, as bicarbonate excretion will be less or will be greater. Thus, for respiratory issues, time of onset is inferred by assessing the amount of compensation that occurred. Now let's get down to numbers. It is time that we review the expected change in bicarb when there's altered CO2, how much the bicarb changes when there is normal compensation, each time the CO2 has moved by 10 from its foundation. With each 10-point elevation, bicarb goes up 1 acutely. Then the chronic compensation makes it 3 quite resolutely. With each 10-point fall in CO2, we answer absolutely that the bicarb will decline as well, and then predict astutely the acute and chronic drops will equal 2 and 4 respectively, as metabolic systems seek to intervene correctively. Well, we're finally done presenting all the concepts you will need when you have to solve a problem and you're eager to succeed. Perhaps it would be wise for us to pause now and review the entire list of questions we have managed to accrue. Number 1. Is the patient's blood acidemic or alkalemic? Number 2. Is the primary disturbance metabolic or respiratory? Number 3. If the primary disturbance is a metabolic acidosis, A. Is the anion gap elevated? B. Is the respiratory compensation appropriate? C. If the anion gap is elevated, can that process account for the entire change in bicarbonate, or must an additional metabolic process, a non-gap acidosis, or a metabolic alkalosis, be invoked? Number 4. If the primary disturbance is a metabolic alkalosis, is the respiratory compensation appropriate? And number 5. If the primary disturbance is respiratory, is it chronic or acute? And now, with no new formulas that threaten to distract us, let's assemble all the concepts and initiate some practice. We'll review 4 cases only, so I won't invoke your curses. Please do each one yourself before returning to the verses. Case number 1. pH 7.24, PCO2 36, bicarbonate 14, sodium 140, chloride 104. The pH is clearly low, so it's an acidemic frolic. Because the keys are low as well, the problem's metabolic. And so 3 questions more we are required now to pose. This really would be easier if I were writing prose. We first must check the gap and ascertain if it is higher. The answer's 22, so we'll say 10 points up from prior. The CO2 says Winter should be roughly 29. The patient's under-breathing, then, a pathologic sign. And if the gap has increased and we know it's 10 points high, we also know that process made 10 bicarbs say goodbye. Let's compare that to the total loss of bicarb from the scene. If normal is at 24, and now it's at 14. That's 10 as well, identical. So now we'll make the call. The A-gap acidosis, by itself, explains it all. There's no need to invoke another process metabolical, and that helps our solution come in short of diabolical. Answer: anion gap acidosis with concomitant respiratory acidosis. Case number 2. pH 7.29, PCO2 60, bicarbonate 28, sodium 140, chloride 104. You know it's acidemia. You know both keys are high. That underventilation has to be the reason why. So we go to question 5. Is all this chronic or acute? Just revisit the equations if you're eager to compute. 2 groups of 10 is just how much the CO2 is askew. Acutely then, the bicarb should be 24 plus 2, and chronically the level should be 24 plus 6. But I chose 28, halfway between them, just for kicks. How should we best explain this unexpected situation? There may not have been time to finish all the compensation. Metabolic alkalosis may have altered the decor, which would mean the baseline bicarb had been more than 24. Or perhaps the baseline CO2 was high, but not a lot. That rise had compensation, but the recent climb does not. Answers: subacute respiratory acidosis with incomplete metabolic compensation, or acute respiratory acidosis with concomitant metabolic alkalosis, or chronic respiratory acidosis with an added acute component. Case number 3. pH equals 7.55, a PCO2 of 40, bicarbonate 34, sodium 140, chloride 104. This case becomes our first one with a pH elevation. Let us welcome alkalemia with interest and elation. I am eager to explore with you this base extravaganza. To analyze it fully, though, I'll need another stanza. It must be metabolic, as the bicarb jump implies. The CO2 is normal, but it should have had a rise. With a bicarb jump of 10, in fact, it should have been 6 more. So some hyperventilation must be added to the score. Answer: metabolic alkalosis with concomitant respiratory alkalosis. Case number 4. pH 7.55, PCO2 25, bicarbonate 21, sodium 140, chloride 105. This again is alkalemia I believe you all will know. It's from hyperventilation, since the keys have gotten low. The CO2 is 15 down from where it ought to be. Is the change acute or chronic? Let us do the math and see. The bicarb drop acutely should be 1.5 times 2. That's exactly what we have here. There's no way to misconstrue. Had the process been more chronic, we will find as we explore, the bicarb would have lowered more, by 1.5 times 4. I just thought it would be fitting, as I ended this review, to give, at last, a one-disorder simple one to you. Answer: acute respiratory alkalosis. This lengthy poem's concluding. That might prompt some disbelief. Had it only happened sooner, you would all have felt relief. But I hope that it was helpful, and if nobody objects, a poem about electrolytes just might be coming next.